Okay, so hello, significantly reduced number of people in class. Your first things first, your take-home midterm is going to be visible in Blackboard at 12:30. It is due in class, printed, handwritten here, not via email. You must be here at no later than 11. Okay, once class starts, I need to have them all up on my desk. No taking extra time to figure that out. So, upgrade. Okay, so here's what you may use. Directions. You are required to work on this assignment by yourself. You may not ask any other student in this class any other question. You may not ask any other professor for assistance. The only questions you may ask are to me. You are allowed to use your class notes and your homework submissions. You're allowed to use the course textbook, which I've listed here, the CMOS VLSI Circuits and Systems Perspective, though pretty much everything in your homework and class notes is sufficient. You may refer to the list of topical guide objectives and example questions posted on Blackboard. You may also refer to the videos that I've posted of our lectures on YouTube. For the last undergraduate problem, and that's lecture notes. All right, here we go. So last undergraduate problem, you're allowed to use Wolfram's alpha tool to plot the delays functions based on the number of stages. So here we have 4 different designs with an 8 input AND gate, and you're to calculate the problem. And in the problem we did in class, you're given n equals 1, n equals 5, n equals 20. And here, you may use the tool and just plot it so you can kind of come up with a range of which design is best for what specific range. So let's go back up here.
Not for this test, but in general, are there programming tools that will help us calculate all this stuff?
Yeah, we're going to be using 2 specific tools. We're going to be using Spice, and we're going to be using Electric VLSI Designer coming up here in a couple of weeks. So what's going to happen is you're going to do this weekend, and then you're going to come up with a draft of your blog post next weekend for those of you who actually submitted a project. And then we're going to start working on, we're going to take the next 6 weeks, and we're going to have a lab that you're going to be working on, where you're going to be basically giving, I'm going to have a set of directions, you follow them, and submit your results. I posted an example plot, which I have here. You can use Wolfram Alpha to type in your plot, and so it actually will reduce it down for you. Don't get freaked out if you actually 4n just becomes 2 times 16, and it comes out 2 plus 3 over n times 3 to 1 negative 1 over n, because it's 3 to the 1 over n negative is just the reciprocal, and that does the same thing here. But these are the correct plots. All right, so failure to adhere to the honor code result is 0 on the exam and possible additional sanctions at my discretion. The take home is you could either do it at your leisure over the weekend, or you could do it in an hour and a half here. So it has to be a more comprehensive exam that's more fair representation of what you learned in class. The other thing important to note, this honor code statement here, you must rewrite the pledge and sign the pledge. So here I pledge my honor, I have not cheated, nor will I cheat on this exam. You must rewrite in your own handwriting, I pledge my honor, I have not cheated, nor will I cheat on this exam, and then sign it. If you do not do that, I will not accept your exam. And then the rest of it is posted. So a lot of it, you'll just be referring to different definitions. Probably all of these should look familiar from before. And then from here, CMOS linear mode operation, critical path problem, stick diagram and transistor layout problem, mobility problem for finding cutoff, linear, and saturation mode. These problems should all look very familiar. An engineer has proposed a circuit as a 4-transistor AND gate with NMOS in the pull up and PMOS in the pull down. I've given you a hint as to where to start the problem. Again, our delays using the tool. And then for this last problem, this is a problem that the grad, Kevin, you are required to do this. All other students may receive up to 8% extra credit for attempting this problem. Consider the 2 design of 2-input NOR gate below. Prove which design is better. Hint, compute the rising and falling propagation delays of a 2-input NOR gate driving H-identical NOR gates using Elmore delay model. So, and I've drawn 2 different designs of a 2-input NOR gate. So that is the take-home exam. It will be visible on Blackboard at 12:30. So it'll be under content. You'll receive a announcement also at 12:30. Okay, so does anybody have any questions about that? Nothing terribly tricky. It's pretty straightforward. Yeah, Adam. Okay. All right. So for those of you who are here, for those of groups who have not yet, for those of you who have not submitted a Verilog or a project proposal, I'm getting a lot of beeps on email, so I'm presuming that's coming by right now. It needed to be done now, so you can still send it to me. You still need to send me the proposal. If you haven't submitted it, you just won't get points. And if you haven't done the Verilog, you're out of luck. I've already granted a 2-day extension on it. So does anybody else have any other questions before? So here's also saying that TGOs aren't doing these people just won't show up. The way this will work, your TGOs that were supposed to be here today, you'll submit them along with your take-home exam. Which, if you do that and you're working on it, you go, oh man, that looks like that problem. You know, that would be very helpful to you. I want you to have them so that way you can use them to actually study for your exam. This one we're covering today will not be due until Thursday. So don't worry about section 4. We're going to start talking about power consumption in circuits until we get to the exam. So in this section, we'll discuss the fundamental theory behind various sources of power dissipation in a CMOS chip. So I wanted to read you a little write-up from Texas Instruments. Reduction of power consumption makes a device more reliable. The need for devices that consume a minimum amount of power was a major driving force behind the development of CMOS technologies. As a result, CMOS devices are best known for low power consumption. However, for minimizing the power requirements of a board or a system, simply knowing that CMOS devices may use less power than equivalent devices from other technologies does not help much. It is important to not only know how to calculate power consumption, but also to understand how factors such as input voltage level, input rise time, power dissipation capacitance, and output loading affect the power consumption of a device. So all of these things all these input factors, you've covered these already. So now we're actually going to learn in this section how they actually input this power consumption. So I've included the source of the document here if you want to read further. We're going to define power as the work done on charge carriers between a potential difference in a circuit over a given time. The SI unit of power is the watt, or 1 joule per second. So joule is energy, seconds are time, potential difference is voltage. So we are potential difference, for example, source from Jane, and we are doing a certain amount of work on these charge carriers that flow through the channel. And so that work that's required to do that, the amount of work done on that over the given time is power. Now, if you recall from previous courses that instantaneous power is power equals current times voltage. We can use this to determine what is the energy, which is the rate of power consumption, is found using the equation E is equal to the integral from 0 to t of the power function P of t dt. And average power is actually a very useful metric to know. Average power of the circuit is the energy consumed by a circuit over a given period of time. It is found by using the equation P average equals E of t is E divided by t. So you just take the equation from 4.2, our energy equation, and divide it by the time and the units for it. So now we have our energy divided, which is joules, divided by time, which is seconds. So joules per second. So we now have power.
That cat seed, is that, are you referring to period?
Yes. The question is, this capital T I'm referring to the period is the rate of power consumption is found over that given time frame. So, as you now know, we can actually relate resistance and capacitance to the actual power consumption of a circuit by using the RC delay model. So we know that this supply voltage VDD, the power generated, is IT times V of t, so the current per unit time times the voltage.
Is that part of the TGO?
No, it's not. The TGO is just the definition. TGO 4.3, define average power. For resistor, we can relate the power consumption to the voltage dissipated across the resistor divided by the resistance, and that is also equal to the square of the current times the resistance. Now 4.4, we're going to relate power stored in a capacitor to previously derived equations. So we know that the current in the capacitor is equal to the capacitance stored times the rate of change in voltage over time. So we have two plates and we're dissipating voltage, and the capacitance is the ability of the device to store a charge. So we're losing charge, and based on that, we have a rate of change in voltage. Applying that to our energy equation, where here in this case it's 0 to infinity, to some arbitrary time frame, P of t dt. We substitute IT V of t, and we have that the current times C dV dt. So then, does everybody have 4.3? So, to scroll for those of you in the back, now we plug in C dV dt into our equation. We know that C is a constant. So then what's going to happen is the voltage of the capacitor is now going to become our VT dV. And the reason we're able to do this is because our DTs cancel out. So now the rate from 0 to the voltage of the capacitor V dt becomes C VC, that should be V squared. Oh, no, it's just VC. V squared over 2. Squared. So VC squared. Okay, so again, this should also be V copied and pasted, so this should be 1/2 CL VDD squared here. So that's the proof. By taking the integral of VT dV from 0 to VT, you get V CL VDD squared over 2. So when we apply so this relates to voltage of the capacitor. When the energy is drawn from the supply, so we have this initial state where we are not drawing voltage from the supply, coming from ground, and we're dissipating capacitor. So half of the energy, 1/2 CL VDD squared. However, when we calculate the energy drawn from the supply, we plug our equation back in, VDD comes out. VDD is also a constant. So that comes out. And then from 0 to VDD of dV, it becomes VDD squared. So since this happens to be twice of that, this means that half of the energy from the supply is dissipated in the PMOS transistor as heat, and the other half is stored in the capacitor. So over the range of the, we have a frequency going in, we have a time frame for one cycle. Half of it is dissipated in the PMOS transistor, and half of it is going to be dissipated by the capacitor for storing charge. There we go.
Is this like a bad connection, or is it?
Yeah, it's just a bad connection. It's nothing I can really do about it. I can try messing with it.
Like this would go idle or something.
No, but it's not idle on the screen. So. All right, so we're going to be learning about 2 separate types of power, and everything else kind of falls into these 2 categories. So the first category is static power consumption. So this occurs when the circuit is not changing voltage. So we have some sort of input spike, and then we have the steady. During that steady, that's what's known as static power consumption. And then during that switch, that's known as dynamic power consumption. So we define static power consumption as occurring when the circuit is not changing voltage, and the equation is static power consumption is equal to the subthreshold current plus the gate current. And we're going to be learning about gate leakage. So you have a general idea of how that actually works. When you have our reverse bias diodes that are supposed to work, we still kind of get a small current back, plus our junction leakage times supply voltage. At 4.6, we define dynamic power consumption as occurring while the circuit's inputs switch. And the dynamic power consumption is equal to the switching power plus what's known as the short circuit current. So we're going to be switching transistors, but then we're also going to be having a very brief short circuit between transistors and the output. And that's why we're going to define short circuit current as the current in a CMOS circuit during the brief instance where both the PMOS and NMOS transistors are on simultaneously. So therefore, we can actually calculate, we can use this to calculate what the switching power is based on knowing these switching, this dynamic power consumption and short circuit. So we have our current, IDD, wave change, times the supply voltage, and then by using our switching power, we have 1 over T. VDD is a constant, so it's the rate over the period from 0 to T of that current. And so therefore, this becomes, we also know VDD squared, right? So we're able to get this CVDD from I of T times the frequency, switching frequency, times T. And T are going to cancel out, so you have the load capacitance times VDD squared times the switching frequency. So therefore, the power consumption, our switching power consumption, is directly proportional to our switching frequency. It has a quadratic relationship with the supply voltage. So what's going to end up happening is a lot of designers are going to try to figure out, and we're going to go into some examples, how to get this supply voltage down while maintaining frequency, being able to maintain performance. Because that's where performance and power consumption are directly trade off. So remember Amdahl's law, we're trying to improve performance by taking certain portions of the circuit and trying to consume and have it go take a certain amount of time. Well, now we're also going to be splitting up into stages, and we're going to do something called voltage staging, where different stages are going to have different power consumptions based on the supply voltage. So the minimum supply voltage required to actually operate the circuit. All right, so does anybody have any questions about this so far? Right now, I'm kind of just introducing the concept of
On the proof, so whenever you integrate over the current,
yes,
your result is TFSW.
yeah, the period, the actual period times the switching frequency times the capacitance times the supply voltage.
So on 4.7, you want us to do that, the chart or the bottom right, all that.
Proof.
Right.
And this is a classic equation, CL times VDD squared times the switching frequency. And so kind of here's an outside the box kind of question. So here's just our switching frequency. What's the energy consumed during that time? What's the relationship between power and
It would be DC, right? DC times that.
E? No.
No.
What's the relationship between, what's the definition of energy?
E equals the integration from 0 to T.
No, what's the word for word definition? With
Energy
4.2.
is the rate of power consumption.
Great. So now we have some sort of time that we're consuming a certain amount of power, right? So then we go back up here, we see that the P average is energy divided by time. So if we're trying to find the energy, we just multiply T times the power. So the power being consumed during a switch is going to be the load capacitance times the supply voltage times the switching frequency times that time. And if you multiply T times frequency, they'll cancel out. So as we showed here, it'll come back out to CL VDD squared. So now we have to know that everything matches up. So another, since static and dynamic power consumption is different, we want to worry about something called an activity factor, where we have some sort of circuit and it switches. Okay, so let's say we're kind of drawing off the example we're going to do. So let's say this is at 1 gigahertz and we have 10 nanoseconds, right? So what's going to happen is we have 1 switch, 2 switch, 3 switch, 4 switches, right? So every time it changes, it's doing some sort of activity, right? So the activity factor is the probability that a circuit node transitions from a 0 to 1. Come on. Computer is up. There we go. So these activity factors denoted as alpha here. The switching factor for an inverter is 0.5. So the switching power, we have multiplying our switching factor times our equation that we follow with here. So this becomes 1/2 times the load capacitance times VD squared times the frequency. And again, it's kind of what I alluded to earlier. E times the power, frequency times D, cancels out 1/2 CLVD.
Let me do D squared.
D squared, good. Copy D squared. All right. So here I've kind of given you the exact example before. Determine the activity factor for the signal below. The clock rate is 1 gigahertz. So here we have 10 nanoseconds. For 1 gigahertz, we know that it's just 1 over 1 gigahertz, so that becomes 1 nanosecond. So here we have 4 transitions, 1, 2, 3, and 4, in 10 nanoseconds. Now, the definition activity factor is the transition from 0 to 1. So 1, 1 here, right? And the reason why it's 0 to 1 is because in digital logic, once we get back here, that's the entire cycle. So the way we're going to actually solve the problem is you count, we have 4 transitions over 10 cycles. Therefore, you just 4 divided by 10, and then you just multiply that by 1/2. So the activity factor of this particular circuit is 1/2 times 4 tenths is 0.2. Does this make sense? So we're going to be using this activity factor to actually relate to the actual power consumption of the circuit. And we're going to be, one of the benefits of knowing this is we're going to be learning about concepts called clock gating and power gating. We're actually going to be using AND gates and inverters and transistors to actually use an enable signal to not allow power consumption past this point in the circuit. Therefore, this circuit will be off when it's not, it doesn't have any kind of activity. So we're going to be trying to turn portions of the circuit off while it's not being used. So, for example, if you recall from my computer advanced digital systems course in computer architecture, where we were talking about draw a circuit that does R-type and low word only, right? And we took out certain portions of the circuit. We took out branch, we took out jump. We only had certain paths. The benefit of being able to do that, other than just understanding the circuit, is that we can actually use power gating techniques and activity factors to say, well, if we're only doing this particular instruction, for example, if I'm just doing an R-type instruction, I only provide a minimum amount of power to the data memory to be able to save the data. Does that make sense? So this is a benefit in power consumption. And we're going to go very briefly at the end of this section into low power architectures. So this is kind of a, I wanted to walk you through this example here of just a series of waveforms. So initially we have an input signal. We start at VDD1, goes down to 0, and goes back up to 1, right? So, and then we have our output where it has some sort of degradation, where so this is an inverter, it inverts, and then after some sort of delay, it comes back here. So here we started talking about this short circuit current, and this is our PMOS transistor current over time and NMOS transistor current over time. So during this switch from 1 to 0, we're putting a 0 on both the PMOS and NMOS transistors, right? So then the PMOS is activated, so we have current. We're going to saturation and we hit linear. So the saturation region corresponds to the switching on the output, right? So then when we hit linear region, we are not switching, we are in static power consumption. Therefore, we're reducing current. And then what happens, if you ever actually can see the screen, we're at this point here, we're actually switching again. The transistor should be off. Any current that's dissipated when the transistor should be off is short circuit current. So it's the same thing. You have like a very small amount of short circuit current here on the NMOS transistor, and here for the other switch, it consumes a lot of current when it goes into saturation and goes back into linear mode. Now, relating this to power consumption, the current of the PMOS transistor, we have VDD minus V out is the power consumption because it's that power difference going back to our initial power equation. And so this is the power rate, the instantaneous power over that time. And then if you want to find energy, you would just do the integral. Same thing with our NMOS transistor. So in our current, we have 0, and then we get to switch. We activate our NMOS. Right? So this is IC equals IP minus IN. So it's activate PMOS, and then our NMOS is kind of the opposite current. And the reason why is because we're dissipating the capacitor on the output. So then our power is just voltage times VC. So this becomes the same thing but a smaller magnitude. And then the energy is just the integral of this. So here it's nothing. So we have 0. We hit here. We have a positive slope. And then here we have negative slope. It goes back down to 0. Right? And then this becomes the power consumed by the supply voltage, and then the energy consumed by the supply voltage. You see that? Does that make sense? Kind of just tying everything together. Hope everybody can see the very light blue. On the video, it should be much more clear. But this is a general idea of how all of these concepts of the integrals and consuming power and using pull-up and pull-down network. And you can see here, power that's created by the capacitor. When we try to reduce static power consumption versus dynamic power consumption, which is here, very small amount of power. And you're going to be learning about, you can use body voltage, trying to change it from 0 to be able to improve the power consumption and having it come down faster. You see how it's 0 and here it's not quite 0? This energy loss relates directly to this waveform here. We're talking about a degraded signal. If we're losing no energy, we get perfect hole and electron flow through the channel, then it would just be a perfect step response. And if you're the reason, if you have lower frequency, you're going to get a better step response. So if you start having higher frequency, you're going to start getting issues such as electron collision, degradation of mobility, and so forth. So this is where all of these concepts kind of tie together. Oh, it was outside. Okay. So I want to take this and kind of use this example question to relate everything to the switching power consumption. A digital system on chip, so SoC, if you ever see that in industry, SoC stands for system on chip. In a 1 volt 65 nanometer process with a 50 nanometer channel length and lambda equals 25 nanometers, has 1 billion transistors, of which 50 million are logic gates and the remainder are memory arrays. So 1 billion minus 50 million is our memory arrays. The average logic transistor is 12 lambda, and our switching factor is 0.1. The memory arrays are divided into banks, and the only necessary bank is activated. So kind of what I was just talking about earlier. The average memory transistor is 4 lambda, and the switching factor is 0.02. Assume each transistor contributes 1 femtofarad per micrometer of gate capacitance. and 0.8 femtofarads per micrometer of diffusion capacitance. Estimate the switching power when operating at 1 gigahertz. So we're going to start out, we have our logic capacitance. So the logic is going to be 50 million, so that's 50 times 10 to the 6, so that's where this comes from, times 12 lambda. 12 lambda came from the average logic transistor is 12 lambda. And then we multiply that by 0.25 micron per lambda, which is what we have here. So our lambdas cancel out. So we have our actual area. Now we also noticed here that each transistor contributes 1 femtofarad per micrometer. So we have this in micrometers here. Micrometers cancel out, lambdas cancel out. So then we have femtofarads. When you multiply this out, it goes from 12 to 10 to the negative 12 to 10 to the negative 9, or to multiply by down. So this becomes 27 nanofarads. Same thing for memory. Here we have 1 billion minus 50 million times 4 lambdas, which is our average memory transistor. Again, times our lambda, so our lambdas cancel out. Again, 1 plus 0.8 femtofarads per micrometer. And that becomes 171 nanofarads. And so the switching factor, we used those two, we were given 2 switching factors in the problem. Let me scroll up just a little bit for those of you in the back. So we're giving 2 switching factors in the problem. We're giving a switching factor for logic and a switching factor for memory. So to work through this problem, we use this equation, VDD squared times our frequency. We know frequency is 1 gigahertz, right? And we know VDD is 1 volt. And then we have our load capacitance times our switching factor. So what we do is we start there and we just bracket them off and sum them. So our switching factor for logic is 0.1. And then we calculated the logic capacitance is 27 nanofarads. And then we add our switching factor for memory was 0.02. And we calculated that the memory capacitance of the 1 billion minus 50 million goes out to 171 nanofarads. We multiply those together and sum them. That becomes our total switching factor times the total capacitor. We multiply that by 1.0 volts squared. That's VDD squared. And then multiply 1 times 10 to the 9 gigahertz. And the total power consumption for the switching comes out to 6.1 watts for this particular circuit. Yes?
These transistors, normal.
Yeah, you need a larger system on chip. Particularly if you're using it to be able to program, like you're going to have billions of transistors in any of these. Right? Yeah.
Like what, 9 million? Something around there?
Yeah. And here's the thing, if we recall from the first day of lecture, right? Well, that's messing around and doing stupid stuff. We're going to recall that our feature size is going down. Our feature size is going down, which means our lambda is feature size divided by 2, right? Because that's poly. So as our transistor size is going down, transistor size is going down, transistor size is going down. Well, we have the same amount of area. So we're just going to put the number of transistors. That's why we have this transistor graph that pretty much went like this. So we're taking advantage of that same area, smaller sizes. Oh, lambda is the feature size divided by 2. Because it's poly. So the thing is, the more transistors you put in, the more capacitance you get. And so that's where you have power consumption. That's why, I don't know if I showed it to you, but if you ever see it in any Intel slides, they'll have this weird slide at the beginning where they'll have the power consumption from the 4004, and they'll come here and they'll say where we're going, and I'll have like a nuclear reactor, and hot, they'll say hot plate here, and it goes up and it just has a sun with sunglasses on it, right? So one of the issues in what people like you are going to be doing once you graduate and get jobs is you have to worry about how to deal with this type of power consumption if we're not going to, and we need to figure out different ways. You have pipelining, you have parallelism, you're using thread level parallelism, and you're actually trying to indicate which ones you're using at any given moment. Turn that architecture off when you're not using it to reduce power consumption. And also, if you're distributing something over a number of threads, we'll kind of go into this towards the end of the section here. But if you're if you have n threads that are doing equal processes, we can slow the frequency down to 1 over n and achieve the same throughput. So, and since we now know that switching frequency is directly proportional to switching power is directly proportional to frequency, your trade-off is power per area. And so, let's kind of give a little more of a basic overview. We have you're synthesizing a chip composed of random logic with an average activity factor of 0.1. You're using a standard cell process with an average switching capacitance of 450 picofarads per millimeter squared. Estimate the dynamic power consumption of your chip if it has an area of 70 millimeters squared and runs at 450 megahertz at VDD equals 0.9. So we have our average switching factor. We just use that equation again. We have 0.1 times 450 picofarads per millimeter squared times 70 millimeters squared. So our chip, you've designed it, you've gone through electric designer, you've done all your optimizations, figured this out. You know that the area is best at 70 millimeters squared, and you know that your average switching capacitance is 450 picofarads per millimeter squared. So, and we know this because we've designed a standard cell. So we've used all of our standard cells. We have our average switching factor times the capacitance of the cells times the total area, the capacitance per unit area, and then millimeters squared. Yeah, but in section 2, we actually did a capacitance per unit area problem. So this is where it kind of comes into play. If you're using standard cell libraries, you can use that to actually estimate the total power consumption of the chip before you synthesize it. Multiplied by VDD squared, here it's 0.9 times 450 megahertz, which is 1.08 watts.
What's the equation for activity factor again? I didn't write down.
Activity factor is you just figure that out by knowing here how many times it switches from 0 to 1 over a given time. So 4.1 is the example problem that describes that. Basically, it's the exact same thing we went through here. So we had 1 gigahertz over 10 nanoseconds, so we know it's 10 cycles, and we had four total changes, 2 from 0 to 1. Therefore, it became 2 over 10, so 0.2. Yes, Trent?
What's the wattage wise when you get too hot? Like work from
It depends. Okay, so that's a whole research field right there. So it depends on what you're applying. You can afford to consume more power if it's plugged in. When you have a phone, you don't want to consume a certain amount of power because the operating system will actually consume a decent amount of power. You don't want somebody to take off their hand, to put their hand on their phone and it burns, right? So our first, they put it on their face and just Steve Jobs' Apple phone goes there for life. Keep it on the phone. So your amount of power consumption is dependent on the actual application. But in particular, for my project I did the smart cards, it has to be powered by the actual energy dissipated by the wireless signal as you have an inductor. So I was doing 6.16 times 10 to the negative 15 joules. That was at 13.56 megahertz. So to kind of tie into, I think you were asking a little earlier about figuring out switching probabilities. So switching probabilities from 0 to 1, right? So for AND, two inputs, it has to multiply your probability on your input of your A input times your probability on B. And the reason why is because it's going to be, both of them have to switch in order to get from that 0 to 1 on the AND gate. So therefore, it follows that the NAND gate is just 1 minus that. It's going to be 1, 1, 1, 0. And 3 is just going to multiply together. Or is this 1 minus not A, not B. So in this case, since it's probabilities, the probability is P of A is 0.4. It becomes 1 minus 0.4, so it's 0.6. And we'll work through an example here. Let me scroll up a little bit so you can get the rest of this table. These are good to know. And it kind of just follows along. NOR is just opposite of this, so it's 1 minus, and then you just have that for NOR 2. NAND 2 just is AND 2 minus 1 minus that. And the next OR is A, B naught, or a plus P naught A, PB, right? And that's because either XOR works where one of them or the other one is 1 and the other, but if they're both 1 or both 0, then it's not. So that's how the probability kind of ties into that. So to calculate the activity factor even further, you can use a further example. So probability is 0.5, right? And then, so PI times not PI. So this becomes 0.5 times 1 minus 0.5, which is 0.25. So the probability, let's say the probability of a AND gate, right, is 1 over 4. So it becomes 1/4 times 3/4, it becomes 3/16. So that's how activity factor ties into probability. And we're going to work through this next example. 4.2 is going to show up. Actually, is it 4.3? It's 4.4. Okay. Yeah. Okay, so does everybody have TGO 4.9? So this should be 4.4. My apologies. Given a 4-input NAND gate as designed to the left, so we have 2 input NAND gates, and then we have our AND gate with inverted inputs, or a 2-input NOR gate. We can actually calculate the switching probability and activity factor at each node if the inputs have P equals 0.5. So we have assumed that all of the probability of the inputs is 0.5 is not being driven by anything else earlier in the circuit. So Pn1, we NAND, so it's 1 minus not A, not B, right? So that means 1 times 1 minus 0.5 is 0.5. 1 minus 0.5 is 0.5. So this becomes 1 minus 0.25, which goes to 3/4. Same thing, it actually solves out because it's a circuit. So now we have 3/4 and 3/4. So just like I wrote up here, the activity factor at node 1 is going to be 3/4 times the quantity 1 minus 3/4. So it comes 3/4 times 1/4, so it comes out to 3/16. Same thing for node 2. And for those of you watching on the video later, node 1 and node 2 are here and here. So then to simplify this problem, if we recall the De Morgan's law again, not A, not B, this circuit becomes not A or B. So then going back up to here, 1 minus 1 is OR, NOR is just not probability of A times not probability of B. So 3/4, 1 minus 3/4 is 1/4. That's where this 1/4 comes from. 1 minus 3/4 is 1/4 again. Sorry, this is killing me. And that 1/4 times 1/4 becomes 1/16. So then our switching factor becomes 1/16 times 5/16, because using our equation we have 1 over 16 times 1 minus 1 over 16. So it becomes 1 over 16 times 15 over 16. and then it becomes 15 over 256. What's that? That escalated quickly? Well, these numbers should kind of make sense a little bit. You have 4 input AND gate, right? It only has switches from a 0 to 1 when all 4 inputs are 0, right? All the switches from 1 to 0 when all 4 inputs are 1, and then from there it becomes 0 to 1. Only in that. So there's only 1 out of the 16 possibilities. So 2 to the 4 is 16. So intuitively, this value makes sense. So then it's just all the combinations that you could possibly have summed up. So switching from 1, so 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, all of that. The probabilities become 15 over 256 because there's only 1, 1, 1, 1, and that can switch from 1, 1, 1 to 1, 1, 0, right? Or 1, 1, 1 to 1, 0, 1. So there's 15 possibilities that that could be. So therefore, our activity factor is 15 over 256. There's 256 possible input-output combinations, and only 15 of them will get that 0 to 1 that we want. Is that, other than escalating quickly, does that now make more intuitive sense as why these are important numbers? So without even doing the equation, we have 5 inputs, AND gate, right? So if we can figure this out, 2 to the 5 is 32, right? So our probability is going to be 1 over 32. The probability is going to be 1 over 32, right? Yeah, so you're doing activity factor. So for this example, we're just ignoring the equation. We're trying to make it intuitively make sense. So that means this can actually go to, 31 from that last 1, 1, 1, 1, 1. So this is going to become 31 times 32 squared. There you go, 31 over 1024. Now does that, those numbers make sense? Okay, so I kind of alluded to this a little earlier, this concept of clock gating. The best way to reduce activity is to turn off the clock to registers and unused blocks. So we have to have some sort of logic that determines whether or not it's actually being used, a controller. We need to eliminate all switching activity. And the reason why is because the clock, every single clock cycle is going to go from 0 to 1 and then 1 to 0, right? So the switching activity of the clock signal is going to be 1. So therefore, the clock power consumption is going to be load capacitance times VDD squared times your frequency. So therefore, clock gating and clock distribution throughout a circuit becomes a very important consideration of power consumption.
What's the typical VDD that they use?
It depends on the supply voltage. So a lot of the questions I'm using are dependent on the as this goes down. For example, 0.25 micron was 3.3 volts, and you get down to 90 nanometers, so that's like 1.8 volts, and then you're getting down to 22 nanometers, which is 0.85 volts. So the amount, by using the equation we learned in section 3 that you're going over on your exam, you're able to determine the threshold voltage required to create the channel for linear mode. And that mode right there, and that difference between the threshold voltage and the output voltage is where they're going to decide that typical supply voltage. So trying to design circuits where you have lower threshold voltage means you can reduce VDD squared is direct on the switching power. So clock gating, to kind of tie in here, you have a clock, and you have this enable logic. The enable logic determines which one. So from architecture, you have certain control signals that go to the ALU out. They're going to memory, right? You have to add another enable logic that knows which ones we want to use. So in section 1, towards the end, I actually showed what's known as a multi-cycle NIPS architecture, which doesn't quite have the performance benefits of, say, the pipeline data path. But the benefit is that the enable logic matches pretty well with the different stages. And so the whole idea is that instead of doing all fetch, decode, execute, memory, and write back, if you're doing an R type, you just do fetch, decode, execute, write back, because you're not accessing data memory. So you're only executing those. The enable logic matches very closely with the control signals that you need. So the ones that you don't need, it just turns right off. Which is why in this course, in lab 5, you'll be given a shell beat verilog of the multi-cycle, and you'll have a couple of things that you're going to want to do. So you won't be expected to do the entire data path for those of you who survive 3 and 5. But then once you get to clock 8, you have this enable logic, and then the clock. Once you have this AND gate, then it goes down to the specific aspect of the circuit. So the 4.10 is just the definition, but the drawing will help you. And so grad assignment 1, this particular magazine article is a description of RTL, register transfer language, clock gating, and sequential equivalence checking. So it's got this a little higher level understanding of how this concept of clock gating is applied to memory and different register levels. So these are a couple methods of reducing power via capacitance. We have gate capacitance and wire capacitance. We know fewer stages of logic reduces gate capacitance. However, we now know that adding more gates can actually reduce delay, because it's an RC delay model. And then smaller gate sizes reduces gate capacitance. Now, wire capacitance is your capacitance of your wire from one block to another block, right? So you have to have good, what's known as floor planning. So recall from section 1, you have your output pins and you have this plan, your cell block. If you have long wires between different portions of it, then you're actually going to consume more power. So you're going to want good planning with where your pins are. So if you're given a cell and you only need this amount of area and you can actually use these 4 pins, you don't want to have something where half of it is actually over here and then just have a long wire. This has a large wire capacity. So good floor planning allows you to reduce power consumption. And so I've given this example. We have 2 energy per stage diagrams here. One of them, this is for what is known as a 64-bit Kogi-Stone adder. Kogi-Stone adder is currently the best adder in terms of performance ever designed, and it uses a lot of propagation and carry logic that kind of goes a step further past the carry look ahead and carry select that we learned in 3, 5, and computer architecture. So in the instance where delay is minimized, so this here, we've simply minimized delay. However, we are getting a lot of increased power consumption because we have nodes in between each adder, and without running out of delay, the high spikes and low correspond to the large gauge driving the long wires. So if you have more of these nodes, you're actually getting these longer wires. So here, they've re-optimized the circuit, and we have a 10% increase in delay. But as you can see, because we reduced the amount of nodes that we need in longer wires, we're going to actually consume significantly less power. So they obtained a 55% reduction in power consumption by trading off only 10% in delay. So again, it matters to your designer. Good design requires good compromises. What your customer actually wants. That is a very good compromise. Nobody got paid. Now, Peter Kogi, this gentleman here, he is also the author of the world's first book on pipelining. He is the inventor of the world's first multi-port processor. processor actually had the opportunity to meet him, the professor now at the University of Notre Dame. And when I was in his office, I just brought up like, oh, I think it's, I was reading up on XQ. He goes, oh, you mean this? And just pulls it up, and it's not even like on a board or anything. It's just sitting there on his desk. I was just like, right, first multi-core processor ever, and he's just showing it out like it's like a pencil or something. It's open.
He keeps it in a coffee mug on his desk. Paperweight.
Yeah, and he has large hairy glasses too and everything.
Was that a picture of the guy in the conference?
No, that was Ivan Sutherland. So yeah, he didn't have hairy carry glasses. He was cool though. For the second grad assignment, and I know I keep encouraging the undergrads to do this as extra credit. This should be pretty fun because this is a layout of YouTube videos of code together of people are building them in Minecraft. Yep. So someone else built a 16-bit ALU, someone built a 16-bit MIPS in Minecraft, someone designed a scientific and graphing calculator in Minecraft. This guy built a whole computer with a monitor and mouse and the whole 9 yards. So if you want to sit there and just see what people have done, pretty crazy. This last link here is how to use Redstone. They use Redstone to actually build these.
One guy did an adder with water, so that was.
Yeah, I haven't seen that one. Adder with water. I can look that up. Okay, so this link is the one that's required for the grad students, but you can kind of just go in there and see how big it is compared to another adder. So let me scroll down here. So voltage and frequency, we now know that based on switching, that voltage is a quadratic effect of dynamic power and frequency is linear. However, we also know that CMOS transistors require certain threshold voltages and voltage differentials to mitigate non-ideal transistor effects. So the diagram that I showed you earlier, we kind of had that degradation on the input and output signal. The faster you switch, the harder it is for these circuits to meet the noise margins in particular. So if you're trying to just decrease supply voltage and maintain frequency, you're going to have a problem at some point meeting your noise margin. So I've also given this whole spiel about operating mode. This actually answers your question. A laptop processor may operate at high voltage and high speed and plug into an AC adapter, but at lower voltage and speed on battery power. If the frequency and voltage scale down to proportion, a qubit reduction in power is achieved. So if you're able to actually reduce frequency and reduce supply voltage, you get VD squared and the additional frequency. Reducing supply. So if that's something that your customers are willing to do, you can go for it.
Go to power saving.
Power saving. Yep. And unfortunately, that's not so smart when you're giving a lecture and suddenly the screen goes blank. So another thing we're going to be learning, this diagram you see down here, I alluded to this a little earlier. We have certain domains that only require certain supply voltages. So because of the design and the number of stages and the smaller amounts of area and the gate capacities, sometimes you can have a smaller supply voltage power the circuit just fine. So in that particular portion of the circuit, you can actually power a voltage domain, which you define here as the area of the circuit where the supply voltage is optimized to the specific needs of the circuit. However, you still have to put all these pieces together, and that's where this becomes an issue. Voltage domain, so here we have a higher voltage domain. I'm going to scroll up a little bit so everybody can see 4.4 while I'm explaining this. I'm sorry, 4.11. So here, the high domain voltage can power the low domain voltage because you're still able to meet that threshold voltage just fine. However, if you have the lower domain powering the higher domain, there's a chance that you will not actually meet that threshold voltage. If you can't meet the threshold voltages, then the result is you won't be able to actually properly conduct the output. So you won't be able to meet your noise margins, you'll degrade your circuit, you consume a lot of power, but you won't be able to convey information. So we're going to be learning here about a voltage domain converter, also known as a level converter. And basically you're using PMOS and NMOS and inverter to be able to step up the voltage. If you're trying to power, it is unavoidable where a lower domain has to power a higher domain. We're going to be learning about a level converter here. So description now in the drawing. So this is actually a level converter. So you have a PMOS, two PMOS transistors tied to the high voltage. So you have some sort of low input voltage coming in, right? VDD-L is powering this inverter. And then you have your input signal and your output signal. When A is 0, N1 is going to be off, and N2 is going to be on. So therefore, N2 is going to pull Y down to 0, which turns on P1. So you have 0, P1 is on, then you have the high output voltage. You're able to create the channel, and then your X value is going to be 1. So therefore, when X is 1, P2 is going to be off. You do the opposite. When A is 1, then you're going to turn N1 on, and that's going to pull down Y, which allows us to get this other transistor on. In either case, the level converter behaves as a buffer and properly drives Y between 0 and VDD-H without risk of transistors remaining partially on. So in this case, this guarantees, by using this difference between high output voltage and low output voltage, that you're able to use this as a proper buffer. So whatever the input is, you're still going to get the same value of the output, but it's going to match to the domain that we drive. So we use these level converters in instances where a lower domain voltage has to drive a higher domain voltage. And so this is actually an issue when you're trying to do low power design and you're trying to do clock frequency and clock gating. You're going to have a little bit of trade-off in area to be able to ensure that you can properly power each portion of the circuit. And another thing for future for design, you have an instance where you've designed a domain to a higher level of voltage, and you design a second domain to a lower level of voltage, right? And they work fine. You put them together, they don't work, and you haven't properly thought about it. Next thing you know, you mix these two together, and it's not getting an output, and if you're not properly accounting for your domains, then you start doing that simulation and tweaking, and then suddenly nothing's going to work because then your supply voltages are not going to tie into that particular domain because you've mixed them. So then you start trying to do these transistor sizes and nothing works, and then you're sitting there for hours and you have no idea what's going on. The reason why is because you haven't properly accounted for voltage domain. Okay, so 4.13 is just the definition, not the drawing. The drawing is there to help. Dynamic voltage scaling is we're using a controller based on the frequency controller and the workload to be able to indicate whether or not we need to be sending the supply voltage to that particular circuit. We can just use dynamic voltage scaling based on the load at any given moment to indicate whether or not we need the supply voltage. And we define it formally as a process which saves large amounts of energy by reducing the clock frequency to the minimum sufficient to complete the task on schedule. Then reducing the supply voltage to the minimum necessary to operate at that frequency. So here we have some sort of core logic that I need to operate. We know that let's recall from previously addition and multiplication, right? Multiplication takes a lot more time than addition. So I can make sure that I have a higher frequency for multiplication to make sure it meets a specific time, but I can have the addition meet the same time by reducing frequency. And therefore, that also becomes very helpful in terms of control logic. But one of the benefits is I know that my workload's lower, so then I can actually cut off particularly in pipelining, you put your output result onto the registers, right? So if you're doing it for an adder, you can slow down the time it takes to do the adder. And once you put the result on the registers, just turn off the ALU. You're not using reduce power. Because if you have it on, you're going to consume the same amount of power for multiplication as an addition. So you can use this dynamic voltage scaling to know if you know the particular operation you're doing in any given moment, you can significantly reduce that power. And still meet the performance constraints set forth by the customer. I should add that. Okay, so next thing we're going to talk about static power consumption. And one of the issues that we have to worry about in static power consumption is this concept of sub-threshold current. So we have not met our threshold voltage, but it's still going to have some sort of current going back and forth. This could happen, and the equations I'll scroll so you can see a big effect is voltage of source to base. So up to this point, we've had this ideal 0 voltage on the base. What happens when the base is no longer voltage equals 0? Then you can actually get this sub-threshold current. Now, Adam, you were talking a little earlier about potential topics. Like, what's this sub-threshold circuit? You can actually use voltage, what's known as body biasing, changing the voltage on the base, to actually be able to manipulate it so you can get the current to generate through the circuit and create a channel sub-threshold. That's pretty difficult, but if you can do that, it consumes a significantly low amount of power.
That article is saying that it could be charged by just a vibration,
Yeah.
solar or whatever.
If you so little. Because you only need a little bit to be able to create the charge carriers through the circuit. So that's what your group chooses to do. That would be an interesting thing. But yet the body bias has to be accurate in order to ensure that you can meet your noise margins.
What's that symbol on the equation?
Oh, I'm sorry, I haven't read the equation yet. So I want everybody to be able to read 4.13. We'll go through this, and we'll go through 4.13. This is what's it? It's got to be 4.5 for example. I'll renumber it. Okay, so subthreshold current is the current that flows through the circuit when it's off times 10 to the voltage gate source plus the Dibble coefficient, the drain-induced barrier lowering coefficient. Drain source voltage minus VDD minus the body coefficient times source base voltage, all divided by S. And S is this concept of stack effect. Stack effect, perfect example, two input NOR gate. So you have some sort of drain current. It's pinched off a little bit, right? Or pinched off mostly. Ideally, you want to completely cut it off. But you have a little bit of sub-threshold current, and then it goes to the next one in series, and that one's pinched off too, right? So if you have them in series, what's going to end up happening is you're going to have instances where it's going to be almost impossible for the current to go through anything. And so we can. It's 12:15, so I should dismiss you. We'll end at TGO 4.14, so I want to. I go 4.15 because I just described stack effect. But I will email this out. This is not due until next Thursday. Because Tuesday is your take-home exam, and yeah. Yeah, the Dibble coefficient. Kevin Lemar.